All right, I'm gonna review the two types of waves, the characteristics of the two types of waves, the formulas and the constants that you need to know for the next assessment. We'll work through these four problems, and then you're going to be on your own. I'm going to get this done. At the top of the screen, you see the two types of waves. If you studied earth science, you're probably familiar with these. But this is, earthquakes are transmitted. The energy of earthquakes transmitted through the earth, either as a compression wave, I think they call it in earthquakes. They also have letters like an S wave or something like that. I don't know. So longitudinal waves are usually waves that are transmitted through a substance, and transverse waves usually occur at the surface of a substance where it interfaces with another substance. For example, the ocean interfaces with the atmosphere, liquid gas interface. Inside the ocean, you have compression waves. But when they reach the surface, the pressurized zones push up and begin to transmit as transverse waves. So there is a relationship between these two, actually. In strings, and you could consider them like one-dimensional strings, cables. The waves tend to be transverse waves. Sound waves through air, through water, even through steel or iron or whatever, they are typically longitudinal. I think I posted a video. I posted a cartoon video about waves. It's mostly about sound waves, but pretty much all the information in it was really applicable to what we're doing now. They talked about how the transmission of sound is faster through solid objects. It's because the particles in solids are much closer than in, say, the air or even in water. And so the pressurized zones of a longitudinal wave, the particles don't have so far to travel to hit the next ones. Sound waves and other longitudinal or compression waves are a lot like dominoes falling. They just bump into the next one and transfer their energy like that. Again, transverse waves are typically like earthquake that are transverse waves or ocean waves. A lot of times those are caused by the compression waves reaching the surface, the interface between the ocean and the atmosphere. But you also get transverse waves on the ocean due to the effect of wind. You could argue that the majority of waves on the ocean are transverse as a result of the wind action. Wind blows across the smooth surface of water, and there's a friction. And so the air flowing over the water begins to ripple the water, and the more it ripples, the more purchase or more friction it gets, and the more friction, the greater it can pile up the waves. Anyway, if you're interested in oceanography, waves are a fascinating, waves, amazing, great source of energy, destructive, but also it's very informative. Waves are very informative. We use waves to transmit information. That's all of our cell phones, Wi-Fi, Bluetooth, all of that is information being transmitted with waves now. All right. So if you look up there, this is not my graphic. In the notes, last class, I give the link where I got this from. You see that the two different kinds of waves have been, they have two different colors, markers showing equivalent parts. So for example, this purple arrow right here and this purple arrow here are showing one wavelength. Now, I believe last class I described what a wavelength was, and I should have. If I didn't, I'm going to say it now. When we describe characteristics of waves versus particles, we use similar descriptors, but rather than use the English language or English alphabet, we often use the Greek alphabet. So for example, the length of a wave is not represented with the English letter L, it's represented with the Greek letter L. This is not an upside down Y, it looks like it, but it's lambda, and it is a wavelength. Okay, so on both of these types of waves, you see one wavelength is described. A wavelength has been defined as the distance between two identical points on two adjacent waves. I don't know if you wrote that down last class. I'll say it again. A wavelength is the distance between two identical points on two adjacent waves. Now, there's other ways of defining wavelength. Your book may describe it as the distance from peak to peak, but it's not just peak to peak. You could go valley to valley. You could go midpoint to midpoint if you know which midpoint you're looking at. For example, if the wave is propagating this way, it looks like it is. It looks like that's an arrow going that way. Then you can say that this is the downhill portion of this wave. So you put a little mark there, and then you find the next place where it's going downhill. There it is, right there. So the distance between that downhill intersection with the midpoint and that downhill portion intersecting with the midpoint, that distance between there, that's the distance between two identical points on two adjacent waves. It's the wavelength. Sometimes you don't have a whole wave, you don't have a picture of enough waves to be able to pick crest to crest or peak to peak. So you have to look at maybe another portion of the wave and measure from there. Sometimes you don't have a picture of an entire wave even. So you might pick peak to valley and double it. And that would be another way of getting wavelength, peak to valley, or intersection to intersection. There's ways of getting wavelength. You don't need the entire wave to get wavelength. And that's kind of important if you go into radio engineering, which could be anything from working on a Navy ship, submarine, could be working for Sprint or Verizon or AT&T and developing better antennas. If you go into communications, radio communications, you're designing Bluetooth systems or Wi-Fi systems, you got to have an antenna to both transmit and receive. And one of the important things about what I just said about waves, you don't need the entire wave to get the wavelength. You do need to know a portion of the wave. And because of that, we can build antennas that are a fraction the size of the wave and still get the information out of the wave, as long as it's a fraction of the size of the wave. And that's important because the antenna is proportional to the wavelength. So right now, you're using your eyes, which are filled with little antennas. They're called rods and cones. They're cells on your retina that contain organic molecules that are basically electromagnetic wave sensitive. And the size of your cells is what has determined what we experience as visible light. The length of the antenna is proportional to the wavelength. And so you and I, as living organisms that have eyes, we see what we see of the electromagnetic spectrum because of the constraints of the size of cells. If you can have a cell as big as an ostrich egg, we might be seeing radio waves instead of, red, orange, yellow, green, blue, indigo, violet, but we don't. We have tiny little cells, and therefore the antenna in it are tiny, and therefore that limits us to what we see as visible light. If you look at your cell phone, you can tell from the size of your cell phone what the wavelength is, because there has to be an antenna inside the cell phone that both receives and transmits, and it is proportional to the wavelength. It doesn't have to be exactly the same size. That's what I was getting at. I'm saying that the antenna has to be a fraction, 1/2, 1/3, 1/4. The closer it is to the full size of the wave, the better the efficiency of the antenna. But you don't need to have an antenna the entire length of the wave to receive the wave and then either double it or triple it or quadruple it to get all the information out of it. So once again, wavelength, the distance between two identical points on two adjacent waves. If you don't have enough of the picture of the wave to do that, you can use a fraction of the wave. You can go peak to valley and double it, something like that. And that's important. That's an important finding. That's an important fact in radio engineering, whether you're working on a Navy submarine or whether you're working for Verizon designing a better telephone, or whether you're working, for some computer company or some Internet of Things company where you're making a Bluetooth, device that connects speakers or whatever. You've got to have antennas, and your antennas have to be proportional to the size of the wave. All right. So in a longitudinal wave, you can see that the wavelength is the distance between the compression zones, two adjacent compression zones. That would be the positive lobes of a transverse wave. Let's stop there for a second. Most people do not draw longitudinal waves, even if they're talking about longitudinal waves. They're hard to draw. All those lines, getting the spacing right. So what people will generally do to represent a longitudinal or compression wave, if you think about it, you could graph the density of the medium You could graph the density of the medium conveying the compression wave. And if you did that, your graph would look like this. Low density, high density, low density, high density, low density, high density, low density, high density. Oh, it looks like a transverse wave when you do that. So most people, when they're analyzing longitudinal waves, will use a representative of that in terms of density versus position, maybe. You know, if you look at the density of the longitudinal wave versus its position, it looks like a transverse wave. So you can actually analyze it as a transverse wave, and yeah, it's easier to draw a transverse wave. Just a little FYI. For the distance from the midpoint to the peak, we call that amplitude. And you can see on the longitudinal or compression wave, that distance is the distance from the center of the low density region to the center of the high density region. It's the amplitude. Now, I'm going to show you what the whole point of this is. We're moving into the electromagnetic spectrum, electromagnetic waves, which tell us a lot about the current understanding of the structure of atoms. I'm going to show you two ways that you can send I'm going to show you two different ways that you can send two photons. Here's one photon. This is a photon. It's a single wave. Let's call it a photon of light. We'll say the distance between here and here, we'll say that distance is 500 nanometers. 500 nanometers. Yeah, 500 times 10 to the minus 9 meters in length. That puts it in visible light. So 400 is bluish light. That's probably, let's see, I got to do this backwards. Probably green, blue, or something like that. You can look in your book, or you can Google what color is 500 nanometer light. What color is 500 nanometer light? It's somewhere between green and cyan, whatever cyan is. Okay, so it's blue. It's somewhere between blue and blue-green. Okay, so that's one photon of light. Now, when we get into Heisenberg's uncertainty principle, I'm going to throw at you a Beightol-ism. I'm going to tell you what I think is waving. I think this depiction of a light wave is really a graph of the density of some virtual particles that we're going to talk about, because it turns out electromagnetic waves do not need anything to wave in, whereas water waves need water, sound waves need air particles or some kind of atoms. Electromagnetic waves don't need a medium. So I have a hypothesis. I have a hypothesis about that there is actually something waving. We'll get into that when we hit Heisenberg next week. Schrodinger and Heisenberg next week. Okay, so that's a single photon of light. I'm going to show you how to do two photons of light. Ready? Here is up, down, up, down, up. There's two photons of light. I'll separate them. You're like, duh, if that was one, then that has to be two. Right, clearly, obviously, two photons of light in succession. Let's see if I can spell that right. Succession, is that right? We would say that that is a duration of light. That's like you turning on your flashlight. Instead of for 1 second, you turn it on for 2 seconds. You've just doubled the number of photons coming out of the flashlight. You've affected the duration of light. So if this is the light coming, if the first one, and I don't know if the people online can see what I'm pointing at the single photon. If that represents light coming out of a flashlight for 1 second, this would represent the light coming out of the flashlight for 2 seconds. It's the double duration of light. It's the same brightness, very dim because I said it was a single photon. Let me see who's knocking on our door. That would be two photons of light in succession. And it's a duration, a time period that the light is on. Here the light is on for example, it's not 1 second. It's crazy to say that's 1 second, but I'm just going to say it. That's like if it's on for 1 second. This is like if it's on for 2 seconds. You get two successive photons. But there's another way to depict two photons. There's another way to depict two photons, and that's where instead of drawing one photon like that, you increase the amplitude, so it's double the amplitude. So the dotted line here represents two photons stacked on top of each other. This is two photons of light at the same time. And that would be called intensity or brightness. Brightness. So if, let's say this is that blue-green light again. A single photon would be dim. If you increase the brightness, if you go over to the wall and turn the dimming switch on your dinner light, your dining room light, you know, some houses have dimmer switches. You increase the brightness, what you're doing is you're increasing the amount of photons produced at the same time, transmitted at the same time. They're stacked on top of each other. Photons are different from electrons, protons, and neutrons. You can literally stack photons on top of each other. So if there were some photons sitting inside this classroom on that chair, they could sit in an infinite number of photons could basically sit in the same chair. Just be very bright. The more there are, the brighter they are. That's what brightness is. The brightness of light is affected by how many photons are stacked on top of each other. So that's two different depictions of two protons. Here we have, I said protons, photons. Here we have two photons back to back. Here we have two photons on top of each other. This is duration. This is intensity. Okay. The last thing I'm going to share with you about, anatomy of waves. Oh, I'm sorry. I just want to make sure this is amplitude, right? So brightness is related to the amplitude of the wave. Volume is related to the amplitude of the sound wave.
So the bigger the amplitude as well.
Yes. The bigger the amplitude, the more waves you have stacked on top of each other. The more units of wave energy you stack on top of each other. Okay?
Got it.
I just want to say something about frequency wave number now. I think I said all of this last class, but oops, I don't want to do that. I'm going to erase all this. Right. If you take physics, you'll learn probably a whole 9 weeks on waves. It's really good. I strongly suggest you take physics. The number of waves that pass a given point, you know, a certain point. Here's the starting point. We're going to have a wave race, okay? There's a string. Here's a starting point. And we set in motion a series of waves, and they're going that way. You can do that by taking like a spring or a rope and just shake it with a certain frequency. And you'll see when you start shaking like a jump rope or a rope or a slinky, if you have a slinky, tie one end of the slinky to the wall and just shake it. You'll see when you first start up, you'll see the wave travel away from you as you shake it. But as you disturb the spring or string and you shake it, you'll see the waves traveling that way. And, you know, or if you're at the beach and you're sitting there and the waves are passing you and you're, you know, whether you're there to body surf or whether you're there to just chill, you can see the waves coming and you can actually measure, count, time, how many go by you within a certain period of time. So the number of waves, and it's generally per second, which doesn't make sense if you're talking about big waves because then you get a decimal number. But if you're talking about small waves, sound waves, light waves, then that number is a very large number typically. The number of waves per second is called frequency. Or we can call it wave number. And the Greek letter that we use to represent number is literally the first two letters of the word number, nu. It's pronounced nu. So it sounds like new. New car. Well, new. That's how you pronounce the Greek letter N. It's the Greek letter N. The Greek letter N is pronounced nu, and it's symbolized as an italic V. It's not a V. It's the letter N in Greek. Maybe you can think about the English letter N in cursive doesn't look the same as the English letter N in standard script or whatever. So this is what we use to symbolize frequency. Some textbooks you'll see a fancy F like that. Also, some books will just say F for frequency. The technical term, the technical symbol is the Greek letter nu. Remember? Greek letters for wave characteristics. Those are the two things that we know in our universe. There are particles in our universe and there are waves in our universe. Each have their own characteristics, each have their own mechanics that describe them. Newtonian physics describe the motion of particles primarily, and wave mechanics describe the motions and behaviors of wave phenomenon. James Clerk Maxwell being one of the great contributors to that. Quantum mechanics is consumed with wave behavior because small particles like electrons, protons, neutrons, and other particles behave as much like waves or sometimes more like waves than even particles. All right, I'm going to get rid of that. We're going to start solving problems. I'm going to be done. I'm going to solve two problems, and I'm going to be done, and I'm going to leave you with the rest, at least half an hour to work on those other four problems. The two formulas that you need to learn for this chapter are E equals h nu. That was Planck's equation that related the color of light to its energy, where h equals 6.626 times 10 to the minus 34 joule seconds. That was the slope of the line. That was the slope of the line that Max Planck discovered related the energy of electrons to the color of the light that produced them. You need to learn this. C equals lambda nu. The general equation for the speed of a wave, the general equation for the speed of the wave, V, not nu, the speed of the wave, the velocity of the wave in general is equal to its wavelength times its frequency. Now that's new. That's why you have to be careful. In general, the speed of a wave is equal to its wavelength times its frequency. Now with water waves and sound waves and other things like that, you can, there's a certain variability to the velocity of the wave. You can speed up the speed of sound by increasing the pressure of the air or the material that is being transmitted through. Sound travels much faster through water than it does through air, and much faster through solids than it does through water, liquids. You can change the speed. In other words, speed of waves is variable for most things. However, with electromagnetic EM waves, the speed is always c. C stands for celeritis, which is the Latin word for very fast. C, you need to also learn 3.00 times 10 to the 8th meters per second. So these are the things that you need to memorize in this chapter to get these kind of problems. There will probably be some other formulas in this chapter, but those are definitely four things you need to know. Two equations, two constants. Any questions about that? I'm going to go ahead and start the first one. What is the wavelength? They want to know wavelength. What is the wavelength of a 2.99 per second wave? S minus 1 means per second. That's a term of frequency. That's a term of frequency. When you see S minus 1, it means 1 over S. S to the minus 1 power means 1 over S. It literally means per second. So if they gave us frequency and they're asking us for wavelength, well, we'd have to ask, well, what's the velocity of the wave? Because the formula for that is here. And I'm going to assume that we're talking about an EM wave, electromagnetic wave. Therefore, C, 3.00 times 10 to the 8th meters per second is the speed of light, the speed of electromagnetic waves, is equal to the wavelength, which is what they're asking for, times the frequency, times 2.99 per second. This is a basic algebra equation. This is algebra 1. We have a variable times a coefficient, and they want to know what the variable is. So we will divide both sides by the coefficient. And look what happens. Of course, the coefficient cancels out. That's why we did that. But over here, notice that seconds cancels with seconds. And we end up with just meters. Hey, that's the unit of length. Meters. That's what we're asking. So we basically have 3 divided by 3. 3 over 2.99 is essentially 3. It's essentially 1. 3 over 3. I mean, 3 divided by 2.99 to 3 sig figs is 1.00. The answer is 1.00 times 10 to the 8th meters. In other words, it's 100 million meters long. It's a large wave. That's some kind of crazy radio wave from some star or something. Who knows? It's fictitious. Does anybody have a question as to how I got lambda? Are you still awake online? Are you able to do algebra 1? You hear the sarcasm dripping from my voice.
I kind of got it. I get the concept just a little bit. Got confused.
Yes. Well, basically what we have here is we basically have C equals Y times X. They're providing us with Y, and they're asking what X is. It's basic algebra. It's not even a polynomial. Let's do number 2. I'll do number 2, and then I'll jump down to number 4 and call it a day. You guys gotta get the last 4 done. Number 2. What's the frequency? That's a song by the group REM. What's the frequency, Kenneth? What is the frequency of a 1.78 times 10 to the minus 15 joule wave? Okay, joule, J, is a unit of energy. Now, many of you have used some form of joules in your life without knowing it in your expression. We're all using joules of energy every day without knowing it, but many of you have actually described it verbally. And here's why. 1 watt. Have you ever heard of a watt? Like a 40-watt bulb or a 500-watt microwave or a 25-watt speaker or something like that?
Yes.
1 watt equals 1 joule per 1 second. A watt is the rate at which you're consuming energy in joules. So if you have a 40-watt bulb, say, Mom, my bedroom light has burned out. I need a replacement bulb. And she'll say, well, what size is it? And you'll say, it's 40 watts. It's 80 watts, whatever brightness you want in your bedroom. 40 watts literally means 40 joules per second. My little microwave back there is a 500-watt microwave. It beams 500 joules per second of microwave energy. I can actually do the math, knowing characteristics of water. I can actually tell you, I can predict for you how long it should take to heat up 200 milliliters of water or a mug of water for coffee or hot chocolate or whatever. I can calculate it. Then I can compare it and I can tell you how efficient my microwave is. It's very simple. Because a watt is a joule per second. 500 watts means 500 joules per second. It takes 4.184 joules of energy to heat 1 gram of water, 1 degree Celsius. Very simple calculations you can do with this stuff if you care to. Somebody's got to make this world. Somebody has to learn this stuff. All right. So we have a joule of energy, and the question is, what's the frequency? Well, look up here at our equations, and we can see that we actually have an equation that relates energy to frequency. So we don't have to do anything fancy here. Another algebra 1 problem. This problem says y equals mx. If you can solve y equals 3x, what's y when x is 2? 6. If you can do that, then you can solve these problems. The only reason why you can't solve these problems is because you don't care to. The number 2 predictor for how you're going to be financially for the rest of your life is how well you have mastered high school math, not college math, high school math. If you make it your business to ace high school math, the prediction is you will be quite comfortable financially for the rest of your life. The number 2 predictor. Number 1 predictor is your last name. If your last name is Gates or Buffett or something like that, you're going to be wealthy. Number 2 predictor is how well you do.
How much you listen to Gates?
There you go. That'll do it for sure. I'm lying. There you go. That's one of those causality, cause effect, logical errors, right? Okay. Covariance, not just causality. So we have a frequency. Oh no, we want a frequency. We got energy. So we have 1.78 times 10 to the minus 15 joules equals h times frequency. We want frequency, so we better divide both sides by h, and we get frequency by itself. H is 6.626 times 10 to the minus 34 JS. Look what happens to joules. Joules cross out, and we get per second, which is a unit of frequency. Plugging this into my calculator, I would do 1.78 EXP I would do change of sign, 15. I would hit the divide by, and I would hit 6. I'm going to say 6.626 EXP. Change of sign, 34, and I'll hit the equal sign. That's how you punch that in your scientific calculator. Now, if you do not have EXP, remember these are the keys for scientific notation, EXP or EE. If you do not have those signs or those buttons, if you have this stupid button on your calculator or something less than that, you must put in here open parentheses or you will get an error. And you need to put your closed parentheses there or you will get an error. Stephanie, right? Are you okay? You look lost. You have a calculator? Can everybody pull out their calculator? Punch this in and show yourself that you can do this because I'm about to sign off. I'm about to go away. Solve that problem. I wrote out, all you got to do is follow it like a little gerbil. Hamster, punch the buttons, get your food nugget out. The keystrokes might be a little different on your particular calculator. I hope you've used it enough times since school started that you know those differences without requiring me to tell you every single time.
Which one is it again?
What's that?
Which numbers are they again? What am I supposed to put in?
What numbers are what? We're solving this problem right here, and I have spelled it out right here. That is the procedure to punch that calculation to get frequency. Well, we're going to round it off to 3 sig figs.
What would be 2.6?
Yeah, 2.69 times 10 to the 18th per second is our frequency. Guys, I'm going to call it there.